So how many different meals can you create from these choices? And you've got two choices of appetizer. I don't know what's a good appetizer. Maybe like shrimp or soup. I don't know, just coming up with something. Three choices of entree, and your entree might be like chicken, beef, or salmon. And three choices of dessert. Maybe your desserts are like cheesecake, brownies, or fruit. I don't know. And so I'm trying to think of all of the different ways I can combine these to make a unique meal. And so maybe you choose shrimp and then chicken and then cheesecake, shrimp, chicken, and then brownie, shrimp, chicken, and then fruit. Or shrimp, beef, and cheesecake, shrimp, beef, and brownie, shrimp, beef, and fruit. And you could, if you want to, make a little tree diagram. But hopefully you kind of see the situation right away is the number of possibilities, the number of possible combinations is going to be 2 times 3 times 3, which is 18 choices. Because every time I reach an independent decision, my tree is going to branch off that many different ways. And every time it branches off that many different ways, it's just multiplying the number of choices you have. So 2 appetizers, 2 entrees, 3 desserts. Sorry, 2 appetizers, 3 entrees, 3 desserts. That's 2 times 3 times 3. That's 18 different choices. Pretty simple. So we're counting the number of combinations. Next question, exercise 2, says, suppose you're a traveling salesman and you need to drive to 5 cities this week to meet different clients. Since you are responsible for making your own schedule, you can put those 5 cities in any order you like. How many different ways could you do this? How many different choices do you have for scheduling these 5 cities? You know, so I could go start here and then go here and then go here and then go here and then go here if I want to. But how many different ways? That's the question. Can I plan this route? I heard an answer, but it was very quiet. 35? Why do you say 35?
Because 5 different cities are like a week is 7 days.
Yeah? That's so 5 times 7?
Every day
So I guess the idea, what I meant by this question is like, you only travel to each city one time.
in one day or 1 week. Like,
And it doesn't really matter what the time period is. You're not going to repeat a sales meeting. You're only going to have like a sales meeting one time and then you'll move on to a different client. And the time period is not important. Like you could do this over the course of a week or the course of a month. But the idea is you're just going to travel to 5 cities in a particular order. How many different ways can you do that? This is how you should think about it. There's one city that you are going to visit first. And then there's another city that you're going to visit second. And there's another city that you're going to visit third. And there's another city that you're going to visit fourth. And there's another city that you are going to visit fifth. Okay? That's what I mean by like putting these cities in order of how you're going to travel between them. So, yeah.
So is it like the first time I can go to 5 cities, then the second time I can go to 4 cities, then the third time I can go to 2 cities?
Exactly.
Okay, so it's 1 times 2 times 3 times 4 times 5.
Yeah, exactly. Yeah, you totally got it. So the first time, I've got 5 different choices, right? And then you just, I don't know, pick one to be the city. And then for the second city I visit, I no longer have as an option city C. I've got to choose from only 4 choices. And so I don't know, maybe I choose A. And then for my third city to visit, I've already visited C and A, so I only have 3 more choices to choose from. And so maybe I choose city D. And then for my fourth city, I only have 2 choices. So let's choose B. And then for my fifth city, there's only 1 of them left. So in terms of the number of choices I have, I've got 5 choices times 4 choices times 3 choices times 2 choices times 1 choice. So
20.
Yeah, 120 different options. Okay, that makes sense to everybody? So you multiply all the numbers together in this descending pattern. And that's how you put things in different orders. We have a name for this. So these are vocabulary words you should know. A permutation of a set is an arrangement of its elements in order. So if I have a set of 5 cities and I arrange those 5 cities in order, I just found a permutation of the set of 5 cities. A factorial is a math function that's defined for positive integers in the following way. So like 4 factorial is 4 times 3 times 2. 5 factorial is 5 times 4 times 3 times 2. You can multiply times 1 at the end if it makes you feel better. You know, you can say 5 times 4 times 3 times 2 times 1, because multiplying by 1 doesn't really do anything. And so if I had the number 50 factorial, that would be 50 times 49 times 48 times 47 times 46 times 45 and so on. And you can recursively say that this would just be 50 times 49 factorial, right? But that's how factorials are defined. 1 factorial is 1 by definition. Two factorial is 2. And I don't think it'll ever come up in this class, but conventionally mathematicians have always said that 0 factorial is 1. Maybe that's not important today, but if it were important, then 0 factorial is 1. That does become important in other math classes, like if you ever were to take a Calculus 2 class. We'll need to know that 0 factorial is 1 for that kind of thing. So we decided to give factorial a name because it shows up as the solution to permutation counting problems. And we decided, well, that's important enough to give it a name. If you ever see this written out, then we call it 7 factorial. That's how you read it out loud. Man, there was a great joke. I'm going to try to find this joke for you. It might take me a minute. I just don't remember where it is. Like it might be in my Calculus 2 notes. Oh well. We'll have to forget it for now. Man, it's really going to bother me if I don't find it though. Let's pull up Google Images. And then we'll search, what was that? Fruit, drink, 42 factorial. There it is. That's the joke. If you can't see in the back, it says, how many strawberries did we squeeze in? 22 factorial, plus 1.5 bananas. And the joke is, how did they even find 1.12 quadrillion strawberries? Because 22 factorial is a really big number. 22 times 21 times 20 times 19 times 18, so on. Factorials grow really fast and make really, really big numbers. So, okay. Onto the joke. You're judging a chili cook-off, and there are 10 competitors. You have to rank all 10 chilies on your scorecard before turning it into a voting system. How many different ways can you put 10 chilies in order? If you have to rank all of them, how many different ways could you fill out your scorecard? It's the same question. The answer is 10 factorial, whatever that happens to be. Should be a pretty big number.
So is it like 10 times 9 times 8? Right.
Yeah, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. It's a lot of different ways.
So on the test, would you just want us to put like 10 factorial, or would you want us to write the answer that?
On the test, I would like you to get out your handy dandy calculator and do 10 times 8 times 9 times 7 times 6.
35. So like 35 times 34 times 32. Right.
Yeah. If you got such a big number like 35 factorial, then don't worry about it. Just write 35 factorial. I guess that's a good question. You can just leave your answer as factorial on the test. How about that? You can just leave your answer as 10 factorial and I'll understand what it means. Yeah, because I'm looking at your calculator now and there's not a factorial button.
So if it's like a smaller number that we can do, if you would want us to do it, but if it's like...
Yeah. It'll probably be a small number on your test. 10 factorial is not a small number, right? But on your test, I'll probably give you a really small number. Yeah. Yeah, I already calculated this. This is right here. The factorial is a real thing. In Microsoft Word, you can type in the letters fact to get the factorial. Like factorial of 10, boop. That does the same thing. So Excel knows what it's all about. New question. This is a good one. Your toddler is playing with blocks. And there are 5 unique blocks. There is a red block. There's a blue block, a green block, an orange block, and a purple block. Your toddler's tiny hands can only hold 2 blocks at a time. How many different ways can your toddler choose 2 out of the 5 blocks to hold? This is a small enough problem that you could just like put your fingers on the blocks and pretend you're holding them, right? You could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You count the same as me? 10 different ways?
So did you do 5 times 2?
Yeah.
So is 5 times 2 just happen to work out in this one, and it usually won't?
You're right. 5 times 2 is a pure coincidence here. The answer is not 5 times 2. No, it's not. 5 times 2 is not the answer, even though it is the answer. That's just purely coincidence. I'll give you another question. I'll explain it. Calm down. You go to compete in a golf tournament where there are 12 total golfers. They divide up the golfers into groups of 4 that travel the course together. The first group of 4 that's going to play through the course, starting from hole 1, is selected at random. How many different ways can you choose 4 out of the 12 golfers to be in group 1? So where are my know-it-alls that said we could just do 4 times 12 is 48 different ways? Right, that's not the answer. 4 times 12 is 48, but that is not the answer.
Is it 12 times?
Is not the answer. There's a lot of different ways to do this, right?
Is it 12 times 8 times 4?
It's not 12 times 8 times 4. So this is tricky. In fact, this is so tricky, I'm not expecting anybody to get this answer right before I explain it. Now here's me explaining it, okay? You ready for a good explanation? We're going to start by placing these 12 golfers in order. We're going to just order them and number them off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? We've numbered them. We've placed them in order. What we're then going to do is draw a line between golfer number 4 and golfer number 5 and say these guys are going to make up the first group. And these guys, the 8 on the right, are not going to make up the first group. Okay? So how many different ways can I put the golfers in order from 1 to 12? We've done this problem before. How many different ways can I place 12 different golfers in order from 1 to 12? 12 factorial. Great. There's 12 factorial different ways I can place the golfers in order, but that's not the answer to the question. The trick now is I've placed them in order, and I'm drawing this line between number 4 and number 5, and I do not care what the order of the first 4 golfers are. I know they're going to belong to the same group, and it doesn't matter if this guy's number 1, or if this guy's number 1, or if this guy's number 1. Who cares how I numbered them, right? The numbering was just a trick to get 4 of them, but now that I've already decided what the group is, I don't care what that number is. And so I'm going to go ahead and say, and this is going to be my answer to the problem over here. It's going to be 12 factorial divided by 4 factorial. Why would I divide by 4 factorial? Because there are 4 factorial ways that I can put the first 4 golfers in order. 1, 2, 3, 4. And I don't care what order they're in. So if I were to take this 12 factorial and place them all in order, there's going to be 4 factorial outcomes where the starting 4 people are actually the same, but I've just permuted them differently. And I don't care how they're permuted. So I'm going to divide by 4 factorial to end up getting rid of the different permutations of the first 4 same golfers. Okay, what else do I not care about? I don't care about how the last 8 golfers are placed in order. I know they're not going to be part of the first group, and I don't care if this guy's number 5 or if this guy's number 5 or if that one or that one is number 5. Don't care. So I'm also going to divide by 8 factorial because in my list of all of the permutations, there's going to be 8 factorial different outcomes that have the same 8 trailing golfers in different permutations. So I don't care about those. And to, pare down my numbers of different outcomes that are, significantly different in this case, I have to divide by 8 factorial. And so this is the final answer. It's going to be 12 factorial divided by 4 factorial divided by 8 factorial. And that means 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 divided by 4 factorial, which is 4 times 3 times 2 times 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3. And you'll notice that some of these things cancel nicely, like the 3's. Ooh, canceled. 4's, canceled. 5, cancel. 6, cancels. 7's, cancel. 8's, they cancel. And so what I get left with is 12 times 11 times 10 times 9 over 4 times 3 times 2. 12 divided by 4 is 3. 10 divided by 2 is 5. 9 divided by 3 is 3. And this is like, I don't know, 9 times 5 is 45. So that's like 495. Kyle.
Why did you not continue down to 2 on the top?
Oh.
I know they cancel out.
Yeah, you're right. You're right. I was just
You kind of forget the 1.
I was just making an error. You're absolutely right. The factorial does go down to times 2 times 1. I just I should have put that. Yeah. So this is, like I said, it's a really interesting question, I think, and this is maybe the trickiest thing to think about. The good news is if you're really confused by this, like, that's fine. You just need to know how to do it on the test. You don't have to explain it to anybody. But I'll try one more time at explaining it. We put all of the golfers in order, 1 through 12, so that they're all lined up. we draw a line between number 4 and number 5, and that way we've isolated 4 golfers to be in group 1 and 8 golfers to not be in group 1. Now, not only have we divided them into a group and not in the group, but we've also placed them in order, and that's going to generate a lot of different outcomes where we're just permuting the first 4 and permuting the last 8, and I don't care about what order they're in. So to get rid of all of the outcomes that are essentially the same for what we're doing, we have to divide by the number of ways to permute the first 4 and divide by the number of ways to permute the last 8 golfers. And dividing by those numbers will get rid of the outcomes that are essentially the same and only leave us with outcomes that are distinct in ways of grouping 4 golfers, ways of choosing 4 out of the 12. Again, that's the explanation. You don't need to know the explanation. What you do need to be able to do is say, well, I have 4 golfers I'm choosing out of 12, so I'm going to write 12 factorial, the total group size, divided by 4 factorial, the number of golfers that I'm choosing, and divided by 8 factorial, which is just 12 minus 4. Okay? And then be familiar with your factorials, and then know that some of them are going to cancel, and that makes it easier. And then a lot of times you don't even need a calculator if you just see that like 12 divided by 4 is 3, for example, and you can simplify this enough to make it happen. But you also do have a calculator, so you might as well use your calculator. Any other questions about this one? No questions? So then let's revisit this. I've got 5 choose 2, right? 5 total blocks where I'm choosing 2. What we're essentially doing here is taking these 5 blocks, putting them in order, 1, 2, 3, 4, 5, of which there's 5 factorial ways to do that. And then we draw a line between the first 2 and the last 3, because we're trying to pick up 2 of the blocks. But I don't care how the first 2 are ordered, and I don't care how the last 3 are ordered. And so this is going to be 5 factorial divided by 2 factorial divided by 3 factorial, and that's 120 divided by 12, which is 10. The fact that it was 2 times 5 is purely coincidence. The real answer is that. Okay, so there's a name for this too. The vocabulary word for mathematicians is combination. A combination of a set is a subset of its elements in no particular order. The way that choosing 2 blocks out of 5 blocks is a subset of the blocks. Choosing 4 golfers out of 12 golfers is a subset of the golfers. And I don't care about the order. The binomial coefficient is a function of 2 positive integers that we normally call n and k. So if I write this is called n choose k. And it's also called the binomial coefficient. And the binomial coefficient is n factorial divided by k factorial divided by n minus k factorial, like 12 factorial divided by 4 factorial divided by 8 factorial. Gave me the 495 in the previous example. And again, this only has a name because it appears as the solution to these combination counting problems, and mathematicians decided, yeah, that's important enough, we're going to give it a name so that we can refer to it later when it becomes important. Okay, so we've done a few counting problems. We're in the middle of learning how to count. You're eating at Genghis Grill, and there's 8 different types of protein when you go through the line at Genghis Grill. Only 3 of them can go into your wok bowl, so how many different ways can you choose 3 out of the 8 protein options? Now that you know the answer, now that you know that formula, you say, hey, that looks like 8 choose 3. And 8 choose 3 is 8 factorial divided by 3 factorial divided by 8 minus 3 factorial. And that would be 8 factorial over 3 factorial and 5 factorial. So that would be 8 times 7 times 6 times 5 times 4 times 3 times 2 divided by 3 times 2 times 5 times 4 times 3 times 2. Just like before, we're going to have some things cancel out. The 2's cancel, the 3's cancel, the 4's cancel, the 5's cancel. And I can write this as 8 times 7 times 6 divided by 2 times 3. 8 divided by 2 is 4. 6 divided by 3 is 2. 2 times 4 is 8. 8 times 7 is 56. There's 56 different ways you can choose the proteins at Genghis Grill. Any questions so far? Yeah.
So the 8 minus 3, can you just explain like what you're thinking? Like,
Uh-huh. Yep. So when we're talking about the golfers, I said I don't care the order I put them in for the first 4 golfers, and I don't care about the order I put them in for the last 8 golfers. The 8 golfers on the trailing end is 12 minus 4. Yeah. So if I wanted to draw the same kind of thing for the proteins, I would say, let's put these 8 proteins in order. 1, 2, 3, 4, 5, 6, 7, 8. And there's 8 factorial different ways to put them in order. Now I'm going to draw a line between the 3rd and the 4th protein because these guys are going in my bowl and these ones are not. So I'm dividing by 3 factorial because I don't care what order they go into my bowl. I don't care which one's number 1, number 2, and number 3. So I've got to divide by 3 factorial to get that ordering out of the count. And then I have to also divide by 5 factorial because I don't care what order these are in, the ones that don't get into my bowl. Yeah.
So why'd you flip the 3 and 2 on the bottom? Was that just to make it easier to divide?
Yep. I just flipped it because I know 8 is divisible by 2 and 6 is divisible by 3. And so that just made more sense in my head. Multiplication is commutative, so you can do all your numbers in whatever order you find happiest. Good questions. I like the questions. So moving on to a new type of counting question. Let's say you're out visiting your nephew, and he asks you, what are your top 3 favorite Power Rangers in order? He wants to know your favorite Power Ranger, your second favorite Power Ranger, and your third favorite Power Ranger. How many different ways can you respond to his question? And you can't say, go away, quit bugging me. You have to give him a real answer. So first we have to count our Power Rangers. It looks like we have 7 Power Rangers. Dominica, do you watch Power Rangers growing up in Poland? No? Oh, okay. You're missing out on the cultural reference here. So, kind of what we're going to do here is we're going to choose 3 out of 7. In other words, we've got 7 choose 3, which is my binomial coefficient. Then put those 3 in order. Because your little nephew does care about the order of those 3 that you choose. And so altogether, the binomial coefficient is going to be 7 factorial divided by 3 factorial times 7 minus 3 factorial times an extra 3 factorial. Well, every time you've got this sort of question, it always happens that the 3 you're putting in order will cancel with this 3 factorial from the denominator, and you're going to end up with something like 7 factorial divided by 7 minus 3 factorial, which is, of course, 7 factorial divided by 4 factorial, which is going to be 7 times 6 times 5, which is going to be 210. So if you were only concerned about choosing 3 out of the 7, then there would be 7 choose 3 different ways of doing that. But we're not just choosing 3 out of the 7, we're also putting those 3 in order, and that gives me more possibilities. So we multiply times 3 factorial to give me the different ways I can permute the 3 Power Rangers after I've selected the 3 Power Rangers. That's how I come up with my 210. Does that make sense? Okay. So the word that goes along with this type of problem in the exercise is called partial permutation. Because a full permutation means I'm counting the number of ways that I can order the entire set. But a partial permutation is just counting the number of ways I can order a subset. In this case, it was how many ways can I order 3 out of the 7 Power Rangers. And that formula is going to be n factorial divided by n minus k factorial, where k is the number of elements in your subset and n is the number of elements in your full set. Just like in the previous problem, there were 7 Power Rangers, and we were choosing 3 of them to put in order, so we had something like that. Okay. Exercise 4 says, your uncle has no hobbies aside from watching football. He's trying to be nice and make conversation, so he asks, rank your top 5 favorite NFL quarterbacks. And maybe you don't know any besides the 32 starting quarterbacks. And so the question is, how many ways can you respond to this question? And this is a partial permutation question, just like the last one. We've got the formula n factorial over n minus k factorial. N this time is 32. K is 5, because I'm supposed to choose 5 out of the 32 and put those 5 in order. And so this is going to be 32 factorial divided by 27 factorial. And that's going to be 32 times 31 times 30 times 29 times 28. That's something I can't do in my head. So you've got about 24,000,000 165,120 different ways you can respond. I heard some very clever whispering over here. Why did I stop at 28? Why did I just do 32 times 31 times 30 times 29 times 28 and then I stopped? Yeah. The rest of them would cancel out with the 27 factorial in the denominator. All the rest of the factors would just cancel, 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 cancel. Very good. All right, new question. It says, you own 3 identical white t-shirts, 2 identical red t-shirts, and 2 identical blue t-shirts. So, if it helps, you can draw a picture. I didn't know I was so good at drawing t-shirts. Should have taken some art classes in college. Okay, that's what we've got to work with. How many different ways can you wear all of these t-shirts during the course of a week? Pretend you can't tell the difference between these t-shirts. They're so identical that it's not significant if you wear one white t-shirt on Monday and a different white t-shirt on Tuesday, or swap the order. You wouldn't even know. So the answer is this. We're going to put 7 t-shirts in some kind of order. 1, 2, 3, 4, 5, 6, 7. But I do not care about the order of the 3 white t-shirts, and I don't care about the order of the 2 red t-shirts, and I don't care about the order of the 2 blue t-shirts. And maybe you're picking up on this, but if I don't care about the number of permutations of something, I divide by that factorial. So there's 7 factorial different ways I could arrange 7 t-shirts if they were all distinct, but they're not all distinct. Some of them are identical, and I don't care the order in which I put together those 3 white t-shirts. I don't know which one's first or second or third, so I divide by 3 factorial to get rid of those identical outcomes that show up in my counting. And then the same thing for the red and the blue. I don't care how they're permuted, so I have to divide by that factorial to make sure I'm not double counting identical scenarios. And so then this is going to be 7 times 6 times 5 times 4 times 3 times 2 divided by 3 times 2 times 2 times 2. So I see the 3's cancel, the 2's cancel, and then there's some other stuff I can do, like have 7 times 6 divided by 2 is 3 times 5 times 4 divided by 2 is 2. So I've kind of partially canceled out those 2's. Or I could just, maybe an easier way to think about this is like 7 times 6 times 5, and then 4 is 2 times 2. So it's 210. 210 different ways you could wear your t-shirts, if this is what you had to work with. Because you're a big M&U fan and you only have red, white, and blue t-shirts. Does that make sense? So I'll introduce the vocabulary word now. The partition of a set is the sorting of its elements into multiple subsets. the number of partitions of k subsets with sizes in 1 and 2 and 3 ... and k from a set with size n is this formula. What we had before was n equals 7 total days in the week. And what we were doing is we were sorting these days of the week into one of 3 subsets. The subsets are white shirt days, blue shirt days, and red shirt days. So imagine some of the days I wore a white shirt, some of the days I wore a blue shirt, and some of the days I wore a red shirt. And for the days we wore a white shirt, the size of this subset had to be 3 because there was only 3 white shirts. And so maybe this was like Tuesday, Friday, and Sunday. For the blue shirt days, the size of this subset had to be 2 because there were only 2 blue shirts. And so maybe this was like Monday and Thursday. And for red shirt days, the size of this subset had to be 2 because there was only 2 red shirts. And so maybe this was Wednesday and Saturday. So we're taking the set of 7 and sorting them into 3 subsets of different sizes. And that's what fits my formula here. That's what makes this formula 7 factorial over 3 factorial, 2 factorial, and 2 factorial. So it makes that a partition problem. I'll give you another example of a partition problem, and then we'll move on. You are designing a stylish tile border in your bathroom. On hand, you have available 4 brown tiles, 5 blue tiles, and 6 green tiles. I'm committed to drawing pictures because I think pictures really help. Without buying any more tiles, how many different ways can you place these tiles in order? Give it a shot. See if you can solve the problem before I do. It's the same as the previous exercise 5 problem that we worked. It should be the same as the t-shirts problem. Because I can't tell the difference between the brown tiles, I can't tell the difference between the blue tiles, and I can't tell the difference between the green tiles. So in total, I have 15 tiles. In terms of number of brown, I have 4. Number of blue, I have 5. And number of green, I have 6. So when I go to use my formula for a partition, this will be 15 factorial over 4 factorial, 5 factorial, 6 factorial. So we've got 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 factorial divided by 4 times 3 times 2 times 5 times 4 times 3 times 2 times 6 factorial. We say, okay, 6 factorial cancels with 6 factorial. And everything else you could just slog through your calculator. Or you could think 4 times 3 is 12. Get rid of that 4 and the 3 and the 12. What else? 5 times 3 is 15, so you can get rid of the 15. 2 times 4 is 8, so you can get rid of the 8. And 14 divided by 2 is 7. So let's say 7 times 13 times 11 times 10 times 9 times 7. Whatever that happens to be, that's going to be our answer.